electric flux, the notation of the electric flux is phi. Here we are studying the electric field flux phi E. As definition, the electric flux phi E is equal to the field dot the area vectors. Here E is the electric field and A is the area of the plane. We can say here we have like a window, and I want to calculate the flux passes through this window. Okay, the window has area A and E is the flux. We have here the lines of this flux, of this field. Now, just I want to give you the condition of this equation. We can use this equation only if the electric field is constant at any point on the plane. So here E must be constant. Very important condition. Here to the right we have a simple example. The area A, we have E in this direction. This plane has a length A with a height B. So we can say A is equal to A times B. But the A vector must be perpendicular to the S direction. I'm talking here about the direction of A. Okay? A must be perpendicular to the plane. We can say to the plane E, A. So we have this plane and A is like this. The angle is equal to 90. In our case here, E and A, here we have E. E and A have the same direction. So to calculate the flux in this case, we can say flux E equal E A dot A equal to E A cosine theta. Theta is the angle between the electric field E and A. You know, in general, A, we can say in general case, A dot B equals to A B cosine the angle between A and B. This is a scalar quantity, okay? And you know that A cross B is equal to A B sine, okay, is equal to AB sine the angle between them, and this is a vector quantity. Okay, now we study A dot B or E dot A. So this is the general equation. I can give you another example. Let's say here we have a plane. We can say we have an inclined plane, okay? Like this. I am looking from the lateral view. It's a plane. The area of the magnitude of this plane is A, and the vector A is perpendicular to the plane. We have a constant electric field in this direction. We can say here we have E. As you see here, the angle between E and A is equal to theta. As E is constant, we can apply directly the total or the flux, electric field flux is equal to E dot A equal E A cosine theta between E and A. Okay, now I want to give some properties of the flux. We can calculate the maximum flux and the minimum value of phi of the flux. You know that the flux is equal E A cosine the angle theta. The maximum of cosine is equal to 1. Okay? Cosine theta, so the maximum flux equal to E A times cosine theta, and cosine theta must be equal to 1 when theta equals to 0. So is equal to EA. In which case, like the first case, here we have a plane. Okay, it's a lateral view of this window. Here we have a vector, and we have a constant electric field like this. Okay, the angle between E and A equal to 0. So in this case, we get the maximum quantity of flux passes through the window. Here we have flux maximum. And the minimum flux minimum when the cosine theta is equal to 0. When theta equals to pi over 2, 90 degree. Okay, so the total flux must be equal to 0. In this case, when we have the window is like this, and A is perpendicular. We have A, and the flux is directed in this way. So in this case, we have the angle between E and A equal to 90. Here the angle between them equal to 90. In this case, we can say we have a minimum value of flux. Okay. This is a general introduction to the flux. I want to give a simple case. The case when the electric field is not constant at each point of the surface of the plane. So here I am talking about the case where E is not constant. So as you see in the example here, we have a surface. We can take the field at this point is like this, here like this, and you see the electric field changes its direction. So we don't have the same field. I don't talk about the magnitude of the field. I am talking about the vector quantity. We must have the same direction, the same magnitude. Okay? In this case, we don't have the same direction. Okay. So we cannot, in this case, what we have to do to apply the flux equal E dot A, we have to take a small portion, a small element from the surface. At this small element, the electric field has same direction at each point here, like this. Because it's small, so we can have a constant field at this point. Okay? And this small area has dA area as magnitude. We can say here we have small a and small b, dA equal a times b. As direction, dA must be perpendicular to this plane. We have dA. The angle between E and dA equal to theta. On this portion, on this small element, as E is constant, we can apply flux equal EA. As we have a small area, so we have a small flux. For this small flux, we have E constant times the area. It's dA. To calculate the total flux here, we have to do the integration over the surface. We get the final equation, formula of flux, which is equal to E dot dA. Okay? The integration over the surface. This is the general equation of the flux. You can start your calculation from this equation. In the case, you can say here, E dA, we have E dA cosine the angle theta. And if you have another case where E is constant, you can get out E, and you will arrive to the same result in the case if E is constant, flux equal E times A, cosine theta. But in this case, we don't have a constant field. So the flux equal integral E dA cosine theta. Now I want to give just a simple example. If we have a closed surface, okay? I give a simple example like this one. Here we have a cube. This cube is empty. We don't have a charge inside. Qn is equal to O. Okay? It's the principal condition. In the case of a closed surface. Here we have an electric field. The field is like this in the x direction, like this, okay? Like this. I don't want to draw on the figure, just to have a clear one. Here we have x, y, and z, x-axis, y-axis, and z-axis, and the field is directed along the x-axis, as you see in the figure. I want to show that the total flux total in this case must be equal to 0. Okay? In this case, when Qn inside equals to 0. First of all, for this cube, we have 1, 2, 3, 4, 5, 6. We have 6 sides. Okay? To calculate the flux, we have to calculate flux total. This flux is equal to the flux through the area 1 plus flux the area 2 and so on. You see well, the side 1 is the back 1. Okay, you see well here. We are talking to the side back of the cube. And 2 in the front. Okay, this one, 2. 4 down. 3 at the top. We have 5 on the side here. And 6 to the side here. In general, you know that the flux in general is equal to EA cosine theta. Here we have E constant. We can use this equation. In the case, if E and A are perpendicular, we can say the flux is equal to 0. I want to draw A for each one. Here we have at the top, we have A3 up, and here we have E. The angle is 90 between them. So the flux phi 3 is equal to 0. Okay? We can take at the bottom A4. Here we have A4. You know A must be perpendicular to the plane. And here we have E. The angle is 90, so phi 4 is equal to 0. The same for 5 and 6. Here you have E, and here you have A, like this. The angle between them equal to 90. The same for the 6. We can say in general that flux 3 equals to flux 4 equals to flux 5 and flux 6 equal to O, because E is perpendicular to A. Okay? Okay, now we have the flux total of 1 and 2. These are equals to 0. Flux 1 plus flux 2. Flux 1 equal E1, we can say E, because E is constant, times A, we have the same area for each side, the same area, times cosine the angle, we have this side, okay? E1 and E have an opposite direction. So we have the angle equal 180 between them, equal to pi. We can say cosine pi or 190 plus flux 2 equal to EA, and the angle here we have A2 and E, they have the same direction. We can say cosine 0. So EA cosine pi equal minus 1. So minus EA plus EA equals to 0. We can get the final result. The flux total of any closed surface must be equal to 0, and in the condition that Qn is equal to 0.